Well, today I'll be going over the max heap and specifically the Dequeue function and its implementation. So here we have a class for a max heap. We have its array representation and the size, which is the number of elements in the heap. So we have the Dequeue function, which we'll be going over, the bubble down function, which the Dequeue function uses, which is why it's private, and this function do something, which calls Dequeue. So right before that is called, this is the state of the cube. So we have 7 elements in it, which is why the size is 7. And here we have the array of elements. Because these are objects, which are references in Java, I'm using these pieces of yarn to connect them. We also have this representation of the tree, which is a bit more handy. So once we call Dequeue, we want to add that to the call stack. So here's the function Dequeue. So first it has this root variable. So next it's going to check, is the size 0? The size is 7, which is not 0, so that's false. We're going to skip that. We're going to say root is equal to heap 0. So I'm going to set this yarn so we can set that variable. So heap 0 is at 10, so let's set that. Let's connect them up. There we go. That's good enough. And then next it's going to say heap 0 is equal to minus heap minus size. So because the minuses are in front, it's going to reduce the size first. So let's change that. 7, it's no longer 7, it's 6. So it's going to say heap 0 is the element at 6. The element at 6 is the 7. So I want to change those connections with that. So let's do that. Let's just move this over here. And then carefully move this one there, come over there, and the 6, just make sure it's all lined up. There we go. So now they're both pointing at that 7. And then we say heap size is equal to null. So this one at 6, we can just get rid of it carefully. Okay, I'm going to have to adjust that a little. There we go. Okay. So now we can update our representation. So the one at 0 is now this 7. This 10 is gone. So we dequeued it. Let's move this 7 over. There we go. And that's our new representation. Then it's going to call bubble down 0. So let's add that to the call stack. Here's the function bubble down. We have the variables in the function, so we call it with 0, so index will be 0 initially. Then we have larger child left to right, which we have here, which are integers. Then we have the object element is equal to heap at index, which is heap 0 currently. So that is the 7, and I'm going to connect that. Let's do that right now. This one right here. There we go. And there's the connection. And let's start this while loop. So while index, which is currently 0, is less than size divided by 2. Size is 6, so size by 2 will be 3. That's true. 0 is less than 3. So let's start. Left is equal to 2 times index plus 1. That would be 1. Okay. Right is equal to 2 times index plus 2. That would be 2. Okay. Well, right is less than size. Right is 2 and size is 6, so that's true. And the element at index left is less than the element at index right. So let's check if the element at 1 is less than the element at 2. So the element at 1 is 9. It's a bit hard to see. That's 9. And the element at 2 is 8. What is it? So that is false because 9 is not less than 8. So we're going to go this else branch, and we're going to say larger child is equal to left. So larger child is 1. Okay, next, if element is less than it's greater than or equal to the element at larger child, which is 1. So element, if we follow this line, is 7. Is 7 greater than or equals to 1 at 1? which is 9. No, that's false. So we can just exit out of this if statement. Then we say heap at index is equal to heap at order child. So the index is currently 0. So we can change this one to point to 9. There we go. And then it says index is equal to order child. So let's change that, order child 1. Let's change this index to that. Great. And we can update our new representation. So now both 0 and 1 are pointing to this 9. So let's just add the 9 there. Get rid of the 7. There's our representation in the binary tree right now. Okay, let's go back to while loop. Now index is 1, and size divided by 2 is 3, so 1 is less than 3, so that's true. Let's continue. 2 times 1 plus 1 is 3. See, 2 times 1 plus 2 is 4. Okay. If right is less than size, so right is 4, which is less than the size, which is 6. That's true. And the one at left is less than the one at right. So left is 3, index 3, right is 4. Let's check. So index 3 is 3, index 4 is 4, and that kind of worked out. And that's true. So 3 is less than 4, so that's true. So let's do this first part of this statement. So larger child is equal to right. So right is 4, let's set larger child to that. Okay. If element, which remember was, if we follow this along, 7, is less than it's greater than or equal to one at larger child is index 4. Let's check index 4. 4. So 7 is indeed greater than or equal to 4, so that's true. Then let's break out of the while loop. So the while loop is this whole thing. And then right here we say heap at index is equal to element. So index 1. Element is pointing to that 7. So we want this 1 to point to 7. It's kind of crossing over a little. There we go. And then we exit the function so we can kind of get rid of this one. There we go. Let me just fix this up a little. I switched around, that's kind of hard, so we can get rid of this thing. Let's actually update our representation of the tree. So now 0 is pointing to 9. Just the same, and this one has a 7 in it. Okay, let's get rid of this 9. That's our new representation. Here's our array representation, and after bubble down, it just returns the root, which is 10. So that's what this Dequeue is going to receive when it gets called. And that's about it. That's how the Dequeue works. Thanks for watching.